Hi, welcome back. So let's continue. So last time we saw orifice meter. So this class we'll talk about notches. Okay, we'll talk new concept called notches. So notch also again is a flow measuring instrument. So I will be asking myself why to study one more new instrument called notch, V notch. So we already have studied venturi meter, orifice meter. Why one more instrument? So now this venturi meter and orifice meter they work when they're full submerged in water. Okay, suppose we have canals or channel. Okay, so how to find discharge flow rate of a channel or a canal which is not fully submerged, right? It's not fully enclosed. So for that we use notches. So in fluid mechanics lab you have studied V notch. Okay, so you saw there was a V-shaped thing over there. Okay, V-shaped notch was there, and the water was flowing, right? And then at the output you could see two streams of water funneling into one point. Okay, they should funnel into one point. So that was V notch. So today we'll see the theoretical aspect of it, theory part of it. Okay, so yeah, again V notch is a flow measuring instrument. Okay, so in syllabus you have two types of notches, rectangular notch and V notch. So in that you have to study derivation only of V notch. Derivation for rectangular notch is not there in syllabus. Okay, so just let me go here. So I told you we have actually we have many types of notches. Okay, we have rectangular notch. Okay, we just write rectangular. We have rectangular notch. We have V notch. Trapezoidal and so on. It goes on. Okay, so we have to study only these two. In syllabus we have only these two. This derivation is there. This only problems. Okay, no derivation. No derivation for this one. Only problems. So derivation we will study for V notch. Okay. Now like I told you, why one more instrument. Suppose say we have a channel like this. Okay, this is the front view. The 3D will do something like this. Okay, I hope you can imagine. Okay, this is how our channel will look. So water is flowing to this point. Water is flowing in the channel. Now I want to measure the flow rate of this. So we definitely cannot use ratio meter or reference meter for this. So we have to go for notches. So what I'll do, I'll place a notch here. Okay, so my notch will be bigger than this. Okay, this is my rectangular notch now. Okay, this will be my rectangular notch. So what will happen? Water will come, it will accumulate, it will spill over. Okay, now I see the side view of this. So how will the side view look? Look something like this. Okay, this will be a notch. That's your side view. Okay, so water will come. So suppose say initially the water level is this much. Okay, because of the obstruction, the water level will start rising and spill over. Okay, so it will look something like this. Okay, spill over. So this is your water. Okay, now this point is called crest. Okay, this point is called nape, and this is the height which you measure. If you remember in fluid mechanics lab, you should adjust one meter, we should adjust one stick was there. Okay, one clamp was there, one stick was there. We should adjust that to find its h. Okay, so if you find this h, we can find a discharge. How much is the discharge in this? Okay, so what we'll do now is we'll straight away jump into V naught derivation. We'll see the derivation for V naught. Then we'll just see the equation for rectangular notch. Rectangular notch derivation is not there. Only problems you have to study. Okay. So I just write here V naught derivation. V notch derivation. Okay. Derivation for V notch. Okay. So before I begin, I hope you have gone through my notes. So in my notes it is properly explained. But like if you don't want to use my notes, you can use Alke Bansal. I have taken notes from Bansal only, so you can use that Bansal. In Bansal, he has explained everything properly, nicely. Okay, so we can begin now. Okay, so we know you have seen how it looks like. Okay, it looks in the that only says V, so it has to be in the form of V, the notch. Okay, so it looks something we can start here. Okay, we'll write here. Okay, it looks like V. So your V notch looks like V. Okay, and we can draw this with actually something. Okay, behind this there is a water column. Okay, so let's say water is up till this point. Okay, the water is up till this point h. This is the height h. Okay, till here. Okay, so I'll just split this in two parts. Okay, so this is your notch. This is the height h. Now we have to find discharge. Discharge is what flow rate. How much of flow rate is flowing through this V notch? That is what we want to find. How much of water is flowing through this notch? That is what we want to find. Now, in previous derivation, ventimeter, we used Bernoulli's equation. We used Bernoulli's equation to find discharge. What we did basically, we had Q is equal to AB. We found B using Bernoulli's equation and substituted over here. We found discharge. But we cannot do the same over here. Two reasons. One is, you see the cross section area is varying from point O to this point, this above point. So cross section keeps varying from this point to this point. That's why, that is one reason. Second reason, the discharge is not constant throughout the cross section. Okay, it will vary from point O to point H. Okay, it will keep varying, it will keep changing discharge. And also because the main reason, because your velocity at every point is different. Okay, at this point it will be different, at this point different, at this point different. So velocity will be different. And one more reason is, when we applied Bernoulli's equation, we had a pipe like this, and we had all this ventimeter over here like this. Okay, we apply Bernoulli's equation for a streamline. Okay, Bernoulli's equation is applied along a streamline. So okay, so we had one streamline like this. We had a water flow. We applied point 1, point 2. We have applied Bernoulli's equation between this point and this point. But we cannot do that over here. Okay, because it's not a confined flow. Okay, we have layers of water. We have layers of water. One layer here, layer here, layer here, layer here. So we have to use some other approach to find discharge of this. Okay. So now let's take a definition. From definition, we'll start this derivation. Okay, we'll take a definition. Okay, now a definition of discharge is what? dq, okay? Area into, this is our definition of discharge, area into velocity. Okay, now what we'll do is, we'll take a small area here, small strip we'll take area, we'll find discharge flowing in that area, and then we'll integrate from point 2 to point h. Okay, so let's take a small area. Let's say this one. Okay, so we'll find discharge flowing through this area. Okay, let's name this maybe A, B, C, and let's say this is height h on top, and this is dh. So that is dh, this is h, this is h. Okay, now we first what we'll do, we'll find how much of water is flowing through this strip. Okay, then we'll integrate from this point to that point. Okay, so first of all, say dq is equal to area into velocity. So we have to find this area. Whose area? Area of the strip we have to find. Okay, we have to find the area of the strip. So what is the area of the strip? This into this. It is AB into DH. Okay, this is the area. Now we have to find AB. Now AB will vary. You can take anywhere AB. Okay, AB will vary from 0 to h. So we have to take AB in terms of h and h in theta. So let's find AB first. Okay, how we'll find AB? We will take small triangle here like this. Okay, let's take a small triangle O C A. This will be how much? Theta by 2. Okay, and this height will be how much? H minus h. Right? H minus h will be this remaining height. Now we can find AC easily, right? Because yeah, if you find AC, we can find AB. Correct? Okay, so let's find AC. How will find AC? What is tan theta 2? Tan theta 2 is opposite upon adjacent. Adjacent is what? H minus h. So we can find AC. AC will be tan theta 2 by A into H minus h. So that's your AC. But what will be AB? AB is 2 times of AC. Okay, AB is 2 times of AC. So I'll just write directly your area dA. I'll just write dA. Okay, your small area will be 2 times 2 times AC into tan theta 2 into H minus h into dH. So that's just small area dA. Okay, Now we have area, but velocity. How much is velocity? Now v is a function of h, so 2gh. Okay. What is this h? This h from here. This is the h. Okay, from here. Okay, I hope you understand this part. Now we are ready. We have area, we have velocity. So let's plug in both the entities into discharge. Okay. So your dq will be what? Will be 2 AC 10 theta by 2 into h minus h into dh into root of 2gh. That's your dq. Okay. Now this dq is only for this strip, but I want to find for entire section, right? So what I'll do, I'll integrate this. So integrating, I'll integrate it, okay, from 0 to h, okay, 0 to h dh. Okay. So when I integrate here, I'll get q. On this side, I'll get q. Now this is what theoretical discharge. If I multiply by CD, what will happen? I'll get actual discharge. So I'll multiply by CD to get the actual discharge. Okay. This is not necessary to write it now itself. You can write it later also. But I'm just writing it now. Okay. This is what a compulsory step where I CD now. So you could write later if you want. Okay. Right. So let's now how to integrate. Integrate what? H, right? So what are the variables here? dh and h. So we have to integrate h respect to dh. Okay. So rest all will be what common. We'll take them out. Okay. Rest all will take them out. So the steps are there in the book. So in the notes. I think so. We made mistakes somewhere. We have made mistakes somewhere, right? Look at the area. What I got there. It is CD to AC will not come. I'm sorry, AC will not come here. AC will not come. Okay, AC will not come because we are writing for AC. Okay, so it will be this much only. 2 10 theta by 2 h minus h 10 theta by 2 root of 2gh. Okay, now it's correct. Okay, so let's take everything else like constants. Okay, so one of them will be 2. 10 theta by 2 is common. CD is common. Root of 2g is common. Okay, that's it. 0 to h minus h root of h dh. Okay, so I'll just let's try to integrate this. So I'll add like this. So now root of h. Okay, root of h is what? H by h raised to half. So it will be h dot h to half minus h 3 by 2 dh. Okay, now it's easy to integrate, right? So I just erase this part. Okay, this is there in the notes. Okay, just see the notes. Let me just flip the board. Okay, I'll just flip the board. Do it this side. Okay, so what we got? Yeah, Q was 2 10 theta by 2 CD root of 2g integral 0 to h into h half minus h 3 by 2 into dh. Okay, so so let's integrate this. So when we integrate, what will we get? H will be h. This will be 3 by 2 by 3 by 2 minus h 5 by 2 by 5 by 2 equal to h. Okay, now these steps I will not do. Okay, you know, very simple. Just substitute what to do, upper bound minus lower bound, all those things you do yourself. Okay, very simple. I just write the final formula. Okay, so the final formula will look something like this. Q after solving this you can do by yourself. Very simple math. 10 theta by 2 root of 2gh h by 5 by 2. So this is what we have. So you can see Q is a function of h only. So this all constant. CD is constant, theta is constant. Theta we know. Theta is what? The angle between this v. This is the theta. G we know. So only thing we have to measure is h. What is the h you are measuring? How much of water is there above the crest? This point is called crest, right? So above the crest, how much water is there? That you have to measure. So if you measure that, you get discharge. Very simple. So in your notes, you are seeing if we have suppose theta, we have notch whose theta is 90, and who has a CD of 0.6, we get discharge of 1.4 something, right? 1.417 H512. This is what we get. So this was special case. If you have theta 90 and CD is 0.6, if you have this case. So this formula you already used it, right, in your fluid mechanics lab. Now today you saw from where it comes from. So basically you saw the derivation. So this was the derivation for V notch. Now for rectangular notch we do not have derivation. Okay, just you should jump to the formula. Like you should just know. Okay, you should just remember the formula, and you should know how to use it for the problems. Okay, so in the exam will ask you problem on that. They will not ask you how to derive it. Okay, so your Q for rectangular notch is this is for V notch. So Q for rectangular notch is 2/3 CDL root of 2GH. Sorry, 2G only. Okay, there is no H. Root of 2GH 3/2. This is for rectangular. Okay. What is the length here? L is length of the notch. L is the length of the notch. Okay, that's it. So only two things you have to study in this part: V notch and rectangular notch. Rectangular notch you should know the equation. In V notch you should know the derivation. Okay, so that is about notches. Okay, so now what we covered so far. First we saw. So we have three things here, right? Flow measurement. Okay, so yeah, flow pressure. First thing was that. Then volume flow rate. Third is velocity. So this was there in module 1. Module 1, yeah. So this we studied now. So what we studied? Under this we studied venturimeter, orifice meter, V notch, and rectangular notch. Okay. Now this velocity I'll leave it to you. This self study. You have to study only one small topic called pitot tube. Only that you have to study this, so that you have to do yourself. Okay. I have written the notes also. I have given notes. You can watch some other YouTube videos or you can read it by yourself. Very simple. Okay. There's no derivation for this again. Pitot tube, don't study derivation. Study only the concept and the problems. That's it. Okay, pitot tube. Okay. So next class, what I'll do is I'll solve some problems. Maybe 3 or 4 problems I'll solve. So after solving problems, I'll give assignment to you. Okay, then you have to solve it and submit. Okay. See you next class.